And we know now how to talk about these two different types of functions, these power functions and their constant multiples, and exponential functions that are base e, so e to the x, and their derivatives. And we can combine them in some ways. We can add and subtract them, but there are all different kinds of ways that we might be able to combine functions, and maybe not all of them we can take derivatives right now. So for instance, if I had x squared times e to the x, I don't know how to take the derivative of that expression. Right? X squared plus e to the x, that's easy enough. Right? X squared plus e to the x, it's a sum, and I know that the rate of change here, I can just measure the rates of change of each term and add them together. Let's look at a type of function that we know that's a product and see whether the same type of thing would work. Let's take something like 3 times x squared. That's a product. It's a constant product, but it's a product. The derivative of 3 is what? 0. And the derivative of x squared is 2x. All right. So the derivative of 3 is 0. The derivative of x squared is 2x. So is the derivative of 3x squared 0 times 2x? No. Okay. The derivative of 3 times x squared is 6x. So this can't work for products, right? Our dream is busted. Okay. I can't just take each factor and take its derivative and leave it at that. That's not the way the derivatives are going to work with products. Right? Both of these factors are changing or not changing at different rates, and I'm going to need to take both of those functions into consideration and combine their derivatives in a way that is not as straightforward as it was with sums. It may be the end of the month and there will still be people doing this, so just let it be somebody that's not here today. Okay? Instead, we need to kind of see what might be going on. And I'm going to kind of run through a quick kind of geometric kind of description of what's happening. And it won't be super formal, just so we can kind of see where this process is coming from. Suppose I had a box, right? And the width of that box was u, and the height of that box was v. And u and v both depended on some other variable like x, right? So width is u of x, height is v of x. Okay. So you give me a value of x, and each of these functions, u and v, is going to determine some characteristic of this box. And then I would have the box. Right? So you say x is 2, and I say, okay, well then u is going to be 4, and v is going to be 3. They need not be the same thing, but they'll both depend on x in some way. The reason I use a box like this is because the area of that box will be the product of u and v. Right? This is u times v. Now, derivatives aren't about static things. Derivatives are all about changing things. So as x changes, I'm thinking that the width of this box is going to shrink or expand. And at the same time, the height of this box is going to shrink or expand. And they may be shrinking and expanding at different levels, right? So the height, for instance, might change just a little bit. And u, the width, might change by much more. So as x changes just a little, the box is going to change also. And because the box has changed, the area will also change. I've got all of this new area now that x has changed. All this blue area now that x has changed. And derivatives, again, are all about measuring how much is changing. And I need to talk about the area of this weird shape. And so I'm going to do what I am prone to do in finding areas. I'm going to break it up into a bunch of things that I like instead of one big thing that I don't like. So I might break it up like this into 3 little boxes. So there's been some change in the width of the box. I'm going to call that delta U. And there's been some change in the height of the box. I'm going to call that delta V. Right? Change in V and change in U. Notice that they changed different amounts, and they're both, how those things are changing are both related back to those original functions, U and V. So this area is the width. The width is just U times the height, which is delta V. And this box off on the right side, it's going to be the base, which is delta U, times the height, which is plain old V, right? The height of this box is the same as the box to begin with. So delta U is the new width, and this height is the same height we've always had. And then this little corner up here is the changes. It's the product of the changes, delta U times delta V. So if I were measuring how much the product has changed, right? Let's get this. If I want to measure what the change in the product is, I can just add up these blue areas and I'll get how much change there was. So it's going to be U delta V plus delta U times V plus delta U delta V. Now, since we're talking derivatives, and I've got these deltas in here for good measure, okay? I want to know, here's how I might be measuring the change in that product, but I'd like to know how am I measuring that change in respect to? Right? What am I changing, and this is the outcome, right? So the derivative might look like something like this, right? Delta of UV divided by delta x, right? If x changes just a little bit, how is this product going to change? And then I'm going to see what happens as that change in x goes to nothing. That's what I want to do, right? How much is the product changing if x changes? And then I'm going to shrink how much x is changing down to nothing, and that's going to give me my derivative. Okay. So this is just kind of a definition of derivative type of statement. So that's the limit as that change in x goes to nothing. And it's all of that change in the product. So U delta V plus delta U times V plus delta U delta V. And it's all divided by some change in x. I'm just going to distribute this change in x into each of those terms so that I don't have a big fraction, that I have a bunch of smaller things. Okay. So that's going to look like the limit as delta x goes to nothing. And it's U delta V divided by delta x plus delta U divided by delta x times V plus delta U delta V divided by delta x. And now these patterns are starting to emerge that seem familiar. I see that this first term is U, and then there's this ratio of the change in v with respect to x, right? As that change in x goes to nothing. This is just the derivative of v. Similarly, here in the second term, I see it's delta u divided by delta x, and the change in x is going to nothing. This is just u prime. This is the derivative of u. And similarly, here in the third term, I might see that delta v over delta x might be v prime here, or I could consider the other one. So this is going to look like u times v prime plus u prime times v. And the key feature here for the third thing is that as delta x approaches 0, u will also not be changing, right? If x isn't changing, then u will also not be changing. So this third bit is going to look like 0 times whatever v prime is, which is just 0. So I don't have to worry about that third term. Back to the analogy of the box, you can imagine, like, if x wasn't changing, I'm kind of pulling this back in. I'm seeing what happens as these dimensions shrink in. And I might still have something kind of measurable happening here all along this side. And I might have something kind of measurable happening all along this side. But this is shrinking in both dimensions, and it's going to kind of shrink to a point really, really fast. So this is going to add up a bunch of nothing, whereas these sides might add up actual area that's changing. So here is what that limit looks like. It looks like u times the derivative of v plus u prime times v by itself. This we're going to call the product rule. This is how we take the derivative of products. So we go back to our previous example with our busted dream, right? I'm thinking u times v goes to uv prime plus u prime v. So 3x squared should be going to 3 times 2x, right? U, I'll leave the first thing alone, and I'll take the derivative of the second thing, 2x, plus u prime, that's my 0, and then v left alone, and v left alone is x squared. So I'm thinking that 3x squared should be going to 3 times 2x plus 0 times x squared, and that's 6x. Oh wait, that's what I should have been getting. So I have a little bit of confidence that this is going to work out okay. I thought about this generally, and then if I apply it to something that I already know, it seems to work out okay. So that'll be neat. Let's do another one. Let's look at something that got this whole thing spurred off. Y equals x squared times e to the x. So y prime, the idea is that every factor will have its turn having its derivative taken, right? And then the other part won't be changed at all, right? Remember, we're seeing uv go to uv prime plus u prime v. It doesn't really matter the order here, right? This is the same thing as u prime v plus uv prime. Right? I could change the order however I wanted to. But you'll notice that in each of these terms, one of the factors is having its derivative taken, and the other factor is not having its derivative taken. And then you add them up. So the derivative of x squared is 2x. And then e to the x, I'm going to leave alone. This e to the x is the same as this e to the x. and then I will add. And x squared, it's not its turn. It already had its term having its derivative taken. But e to the x hasn't had its derivative taken yet, so I'm going to take its derivative. And the derivative of e to the x is e to the x. So this e to the x is the same as this e to the x. The first e to the x is the same as this e to the x. This e to the x is the derivative of this e to the x. It just happens that e to the x is its own derivative. So it looks like y prime here is 2x e to the x plus x squared e to the x. And that's a fine way to write it. If you really wanted to, you could factor out a like term and add your remaining terms in descending order. Right? Both of these have an e to the x in them, so you can pull an e to the x out, and you'd be left with x squared plus 2x. So it's kind of this exponential function times a polynomial function again. That might help me if I wanted another derivative. Okay? So I could kind of keep at it, right? If I wanted y double prime, well, the derivative of e to the x is e to the x, and the second thing is going to stay the same. And then the first thing stays the same, and I take the derivative of the second thing. And I get something like this. Right? Take the derivative of the first, I leave the second alone, plus I take the first one and leave it alone, and I take the derivative of the second one. Right? Every factor has its turn having its derivative taken, and when one thing has its derivative taken, all of the other factors you leave alone. You don't change them at all. So I could keep it this all day if I really wanted to. Right? Factor the e to the x's out again. And again, I have e to the x times some polynomial. So if I wanted y triple prime, I could use the product rule again. I could do it as much as I wanted to. I don't want to, but I could if I wanted to. So that might be an advantage of kind of rewriting these types of expressions, because future operations might be easier to do if you simplify them in some way. But in general, I'm not super picky. This is equivalent to this, and technically correct is the best kind of correct. It's just I could have. So this is the same thing as x, e to the x, x plus 2. So now I've got 3 different factors. This might have its uses also. Say, for instance, I'm really wondering when a derivative would be 0, because those points seem interesting to me. Right? They certainly were when we were graphing derivatives based on what the original function looked like, right? When a derivative is 0 is going to correspond to these kind of peaks and valleys of a graph. So if I wanted to know when something was maximized, I'd be wondering about, well, when is the derivative 0? So I might want it factored as much as possible. Because if I ask myself something like, when is y prime 0? I could say, oh, well, x e to the x times x plus 2 equals 0. And because this is factored, right, the only way that you get 0 is if one of the things you're multiplying is 0. Right? You can't multiply 2 things that aren't 0 together and get 0 out of it. So this just says x is 0, or e to the x is 0, or x plus 2 is 0. So one of those things has to be true in order for the product of all 3 to be 0. And that means that x is 0, or e to the x is 0. Does this ever happen? And if so, when? When might 2.7 raised to a power give you 0? Never, right? Never. E to the x, if you'll remember the graph of it, it looks like this. It looks like Superman the Ride. So it's never going to touch 0. So this has no solutions. That says no solutions. And then when does x plus 2 equal 0, if ever? At negative 2. So this is x equals negative 2. So here are 2 really interesting points for this function. Okay? Here's a function x squared e to the x. And I know that it might have a maximum or a minimum at 0 or negative 2. Those are potential times of interest for me. Is it guaranteed to have a max or a min at those times? Could the slope be 0 and it not be a hill or a valley? I think so. Can we think of an example? What type of shape would be flat at a point, but not be a peak or a valley? A line won't be 0. I can say a flat line could be 0, right? Yeah. So like if you had a flat line that has no peaks or valleys, but it's also the slope is always 0. Might think about something like x cubed. X cubed doesn't actually look like this. It looks more like this. Okay. X cubed is kind of flat here at 0. So it's just kind of momentarily flat, but then like it keeps getting bigger. Okay? Oh, I'm getting bigger. I'm getting bigger more slowly. I'm not getting bigger at all. Oh wait, I decided I'm going to get bigger again. So this type of behavior is possible. So these zeros don't guarantee max min types of things, but there's certainly an indication that this could be happening. So those are points of interest. All right.